I am really excited to introduce our next Artemis Road speaker, Dr. Ernest K. Lewis. Everybody say hi. Dr. Lewis is the founder, principal scientist, and manager of the Planetary Experiment and Astromaterials Research Laboratory. NASA loves acronyms, so they call that PEARL. And it's part of another acronym, ARES, which stands for Astromaterials Research, Exploration, and Science. And that's at Johnson Space Center, which is in Houston, Texas. Okay, so if you guys ever go to Houston, you got to go to Johnson Space Center and see everything they have there. He does a lot of cool research with a focus on the dark, cold environments that the astronauts for Artemis and the robots that we send to the moon are going to have to experience there in the South Pole. And he's going to talk to us about how his research is helping NASA understand how materials are going to interact in those cold environments. He's got a background in chemistry, a BS in chemistry, and a PhD in physical chemistry. So if any of you guys are interested in chemistry, you can be a chemist and work for NASA. And he's going to talk to us for about 30 minutes about what he does. And then we're going to open up the floor for your guys' questions, okay? If you have a question during the talk, feel free to put it in the chat if it's appropriate. Maybe we'll ask that question at that time. But we'll certainly get to it at the question and answer time after the talk if we can't get to it while he's talking. You can also write down your questions as he's talking, and you can ask it at the end of the talk, okay? So yes, thank you for joining us, Dr. Lewis. I'm going to go ahead and pass it off to you.
Okay, thank you very much. It's an honor to be here with you all today. I really appreciate it. I'm going to share my presentation. Watch out. Let's see. All right. Can you see that okay?
Yep.
Excellent. I cannot see the chat when I'm sharing, so if something urgent comes up, let me know. So I get a chance to talk to you about several missions today, and then some of the things that we're doing in my lab to kind of support various missions or get positioned for those kind of things. And I'm going to start from very general things and then go to very specific things. And I find that method is kind of helpful to get kind of a landscape of what's going on. To talk a little bit about NASA, you know, what does NASA do? I'm sure you're familiar with it in some form or fashion. But in general, a way I like to tell people is that when we do experiments or engineering things at NASA, it kind of helps the country, and it very much helps our human exploration. So what that means is there's a lot of centers around the country that have different capabilities. So if you can see my cursor down here in Houston, Texas, for example, we are the Human Space Flight Center. And what that means is anything that involves training of humans is generally done in Houston. So if you like rockets, for example, if you see Marshall Space Flight Center over here, well, they do rockets. And so if you were to go to Marshall and say, I want to talk about humans, they would say, well, you should go to Houston because Houston does humans. And so each center kind of does a different activity, and overall that kind of helps. The other thing that's kind of fun to think about is that we don't actually send money to space. Sometimes you'll hear people say, like, why do we spend all this money in space? Well, the taxpayer dollars go back into the country to develop the things that we have, like computers and cell phones and all these other technological innovations that we're used to. So that's where I've bolded these two things. The agency shares what it learns so it can make life better for people worldwide. And NASA helps teachers prepare students, which would be you, for the engineers, scientists, and astronauts of the future. So by all means, this is our current, we have many astronauts. The ones that are next to go to around the moon in Artemis 2 is Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. So for Artemis 2, they're going to go around the moon, but they're not going to land. Artemis 3 will be a landing, and that's coming up. I thought I would show you a couple of small videos. I'm going to stop sharing my screen. If you could play video 1 and video 2, they talk a little bit about Artemis programs, and I think they do a lot better than me sharing slides.
Okay, I'm switching the sharing over now.
Okay.
It's a new day in space exploration. As we sail on this new cosmic sea, there's so much to learn. There's so much to be excited about.
Artemis is different from anything humanity has ever embarked on before. And we will discover life-saving, earth-changing science and technology along the way.
We're delving deep into what science can be achieved by humans working together with robotic capabilities and future infrastructure to support a long-term human presence at the moon.
The Artemis generation stands ready to return humanity to the moon and then to take us further than ever before to Mars. Onward and upward.
Did you want to go ahead and go to the second video also?
Yeah, let's try that one. For some
Wonderful.
reason, it comes through a little bit choppy, but you have the links in the chat. And so while you're queuing up the next one, you can see they talked about Artemis to Mars. Both the Moon to Mars program is a very big thing. Let's see how the next one will meet the astronauts that are going for Artemis 2 here. I guess the music seems to get lost on my end. Well, feel free to sing and make up music in your own local areas there.
I'm Jeremy Hansen. I'm a mission specialist. I'm Victor Glover. I'm the pilot. I'm Reed Wiseman. I'm the commander of the Artemis 2 mission to the moon.
To the moon.
To the moon. To the moon.
I don't know if you're getting the voices, but the Artemis 2 mission will be going around the moon. And it's going to lay the framework for people returning to the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. That's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign and missions have set such an ambitious goal for humanity that's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together. When I look at the Artemis 2 crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis 2 is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on Earth. Artemis 2 will be NASA's first crewed flight test of the Space Launch System rocket and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space.
And pave the way for NASA's long-term human and scientific presence on the lunar surface.
We are ready.
We are going to the moon for all of humanity. We are Artemis.
So it's a really big effort, and you can see that there's a lot of elements to this, not only in propulsion and engineering. So even the fact that you are sitting here in the audience paying attention is a contribution, because it shows that we're looking forward, and these things take a very long time. And so one of the things I wanted to make sure for today is kind of reflecting, when I was your similar ages, I was kind of interested in NASA, but I didn't have anybody that said, hey, go do it. You can do it. So I want to make sure that if you're excited about NASA, that I've told you you can do it. So there's a lot of different contributing factors for that. So one of the things that I get to do in our chemistry lab is I get to make surfaces of planets. How do you know what the surface is going to be like, when you get there? Well, the trick that we have is that science is the same regardless of the location, which means we can make experiments and test it for other planets. So I'm going to switch back to my screen here for a second. And I want to talk a little bit about what I do as a planetary scientist. So I'm making a very big jump. We were talking about kind of generalized missions, going to the moon, going to Mars. And now we're jumping back into the lab. How do we test those things? So in the upper left here is an example of frozen simulated lunar dirt. Now on Earth, we call it dirt because it has carbon and other materials in it. On the moon, most of it is minerals, silicas. There are small fractions of various carbon from meteorites and other sources. But in general, it's not like the dirt on Earth. So we use this weird word we call regolith to represent the top layer of the moon. And what I get to do is I get to take this material and make it very cold and then simulate the lunar portions of the moon that are frozen. So I'm skimming over some details, but it's quite fun. And you can see, I have an airbrush and scrapers and various stages. And then I can take these simulated materials and I can put them in my frozen containers, and we can study those. One of the things that we've done is engineered a cryo block system. So this is at minus 200 degrees C, which is very, very cold, and it freezes anything that's sprayed onto it. So that allows us to make these kind of complex mixtures of the lunar surface. So it means that I can simulate the moon in our laboratory, minus the gravity, of course, because that would be a lot more expensive. But it's quite fun. So as you go through your schooling and your stages, there you will find the joyful things in your activities, regardless of if it's engineering, science, those kind of things. So not only can I make simulated surfaces for the moon, but we can also work towards other planets. So I believe we have, I wanted to show you Mars video 3, the video about Mars.
Sorry,
So if
I
you
was
can,
working on a technical issue for another team. I'm sorry about that. Hold on. I'll put
Nope.
it started. I'm sorry.
Oh, it's all good. No worries.
All right, see if this is going to behave this go round.
I don't know if you're getting the audio. I can talk over it. Currently on the Mars planetary surface, we have rovers that are collecting those samples. You see those sample tubes. And the plan is to put it in another lander eventually, and it will put it in this white return vessel that will be launched from a rocket from the surface. So once we've collected our samples, it'll actually be launched up into orbit. And the gravity on Mars is less, so it's a little bit easier to launch things. And it's actually going to transfer the Mars samples from one vehicle to the return vehicle. Imagine playing Interstellar Catch. It's going to be amazing. And that vehicle, that satellite, will then bring the samples back to Mars. So currently, we have not had any Mars sample return missions. This would be a first in that. However, we do have some Martian meteorites simply from impacts and formations of the solar system. So we do have those materials, but in very small amounts. This would be a bigger amount. So again, let me go back to, let's see, I was trying to share my screen. All right, so we are able to go to the moon. We are able to plan for sample returns from Mars. All the samples that come back from Mars or outer space come through JSC in some part. Switching a little bit to asteroids and then OSIRIS-REx. If you can play videos 4, 5, and 6, the video 4 is our mission that we just had for actually changing the trajectory of asteroids. They're called the DART.
One moment.
In case
Sure.
there were.
So recently there was a mission that impacted an asteroid that was orbiting another asteroid. So what's phenomenal is that we hit a very small target.
You can actually stop it. That's kind of fantastic.
NASA is crashing a spacecraft into an asteroid.
What you think science fiction, but this is real. Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen.
I'm Lena Adams. My name is Kelly Fast.
I'm Andy Rifkin.
I'm Justina Srovitz, and I helped tell the story of the DART mission.
I'm a planetary defender.
And I study how the orbits of asteroids change after we hit them with spacecraft.
My job was primarily to make sure all the systems on the spacecraft work together.
The DART mission is NASA's first test of planetary defense technique called kinetic impactor.
DART is the double asteroid redirection test.
It's just a spacecraft that is going to go and smack an asteroid
The moonlet Dimorphos, which orbits the asteroid Didymos,
and see if we can change its trajectory just a little bit.
in order to show that we can deflect incoming asteroids if we need to.
DART will only be changing the period of the orbit of Dimorphos by a tiny amount, but in space, just a little bit is just enough to make an asteroid actually miss us in the event that an asteroid is discovered well ahead of time before it might impact Earth. Behind me, you see the spacecraft.
It's really cool to see it coming together in real life.
It is fantastic to see it in real life.
To see it turn from ideas into real pieces that are gonna go into space.
The solar arrays will actually roll out to 28 feet in length.
Once the solar arrays are deployed, it's going to be the size of a school bus. As the solar array opens up, it's going to swing out in this direction. The asteroid's only 2 football fields inside.
We're flying at over 6 kilometers a second.
30 days out, we see 1 pixel on our field of view.
You can see Didymos and Dimorphos as 1 point of light.
About 4 hours out, our spacecraft becomes autonomous.
And then that's where everything gets really exciting.
You actually are seeing impact.
We're super excited and nervous as well.
I feel really honored and humbled to be working in an area of science that has such a broader impact, figuratively and literally.
No, DART.
the dinosaurs are made completely extinct by an asteroid impact so many years ago. Here we are, we can actually do something about it. I think this is just wonderful.
Going on.
So
to the
that's,
In case.
yeah,
there
go
was
to
an
the next
asteroid
one.
coming towards Earth
Hold on.
there, you can actually
Sure.
stop it. It's kind of fantastic.
NASA is crashing.
Try this again.
So here are 2 asteroid missions.
This is
One
NASA's
we showed,
first mission to retrieve a sample from an asteroid.
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid belt and back.
so Bennu was important as an asteroid because it's mostly carbon. Most of the meteorites that we get from falls to Earth are iron, but we are carbon-based beings. So this actually touched down and go, tag, it touched down on the surface and grabbed a bunch of material and then brought it back to us.
OREX MSA on OREX off. Sample collection is complete and the factory burn has executed. All right.
And when you saw it touch the surface, look at all of the dust and powder that comes up. And that's because asteroids are not necessarily hard packed like we're used to walking on Earth. Once the satellite got close, it released the return capsule, and the satellite is actually going on to another mission.
Medial milestone, we are touchdown. I repeat, medial.
So OSIRIS-REx landed, and you can see it perfectly situated there. And in the last video, if you just go to like 4 minutes, we don't have to watch the whole thing, but I wanted to show you, so once the satellite returned and then was brought back to the lab at JSC, and so that's good. I wanted to kind of give you an insight. So once the capsule was inserted, what we do is we have ultra clean glove boxes. And so each bit of material from that super rare sample is brought back to a clean room that's almost, you could think of it like a surgery room, but perhaps even cleaner than that. And at no time does anybody touch the materials, but the tools touch the materials. And so we're in the process of actually sorting out these very particles, dusts, rocks, and it's not just kept at NASA, it's again returned to the community. There's a lot of coordination going on, a lot of communication, not only between scientists, but between scientists and engineers and companies to make sure that everything is done as perfectly as it can be. So there's a lot of aspects to this. You can see, they slide the samples around to different positioning. I believe they're sliding that to take pictures of the sample. And that's good. We can stop this video here. All right, so I've got a couple of minutes. I will finish and then we'll have some question and answer. So I wanted to come back to, again, what we do in our lab. We're able to make and study these simulated materials because it allows those who are designing the system to test it. So there's a lot of aspects, and what I tried to give you very quickly was very wide view to very narrow view of what we do in our lab. I can make all sorts of different ices out of not only water, but different compounds. So I can make blocks or pellets. I can make in the middle soft ice. I can make ice crystals. All of these different things are on the surface of the moon in some form or fashion. These different mixtures, when you take a microscope, they can have various degrees of water or regolith or dirt in them. So I wanted to give you a short history of our lab, and also just to tell you what kind of things can happen when you are in a supportive environment, which is very good. Ares, Johnson Space Center, is very supportive. We started in kind of a blank space that was being refreshed, and myself and the Ares coordinated, so it started in a blank room, and then we grew to 3 people, and I was able to acquire some funding. We continue to grow. We've had people come through the lab and move on to other departments. Our current group, Christopher Harris, Shoneb Ghosh, Crystal Mantilla, myself, Celia Amick, Jeremy Boyce is our civil servant sponsor. And there's a lot of people working towards just this aspect in the laboratory. So we have our Johnson Space Center, Ares. There's a contract that supports all this, Jacobs Jets. I'm part of the Texas State University system. We're also funded by Survey IS50. Here's our group. And we recently made a logo. And that is it for my content and time. I wanted to make sure we have time for questions and answers. And let me know. Thank you very much.
Thank you. That was
Thank
cool.
you. Yes, thank you, Dr. Lewis. All right, guys. Hopefully you have lots of questions. I see one hand raised already. So yeah, if you have a question, there's 2 ways to ask it. You can raise your hand. I see a group that's already done that. And we'll call on you and you can unmute your video and ask your question. If you're not comfortable doing that, you can also put your question in the chat and I'll go ahead and ask that question for you. Make sure when you put it in the chat, you're sending it to me or to everybody so I can see it. All right. I see Michelle O'Very, or at least her Zoom, has got a hand up. Why don't you go ahead and unmute yourself and ask your question?
We have a couple students with questions.
Great.
So my first question is, do you guys know the exact temperature of the South Pole of the moon? Or just anywhere on the moon?
Oh, that's a great question. I can answer that. And I wanted to bring up a slide, if I may, since we're...
Yeah.
All right. I had another set of slides, just in case you had that great question. All right, can you see my screen?
Yep.
Excellent. So there's several different temperature scales. It's approximately in the minus 400 Fahrenheit, or what we call Kelvin. So 25 Kelvin, if you can see my cursor here, is the little purple areas. And so this is a map of the estimated temperatures of the moon, which is anywhere from, minus 300 Fahrenheit and below. So there's currently a satellite going around the moon called the LRO, and it's imaging the surface of the moon to find those exact temperatures. So that's a great question.
Okay, so my next question is, what do planetary scientists exactly do? Like yourself, like what do you do on just every day at work?
Well, we get to interact with the government, and so we fill out forms. No, I'm just kidding. All right, we get to do some pretty cool things. There is a lot of paperwork involved. A planetary scientist studies the formation of planets, including Earth, and eventually you study the materials, mineralogies, and constructs so that you can tell the story of how that planet or astrobody formed. This is where, as we gather data, we can tell, how old Earth is, looking at what's called isotopes and geochemistry. You can use the same principles to begin to build a picture of how did the moon form? How did Mars form? Not only its formation, but also you can begin to get a picture of what the local history of Mars was. So if you've seen the latest studies for Mars, looking at the different geological forms, it can be interpreted that there was water, flowing water on Mars a long time ago. So that's kind of a synopsis of what a planetary scientist does.
So this is my last question. Why you showed us a picture of the ice under a microscope, and why was the ice so dirty?
Another good question, y'all. So I'm purposely mixing it with the dirt to simulate that cold temperature of the cold regions of the moon. Those cold regions of the moon are called permanently shadowed regions, and basically they're always in the dark. And so one thought is that as they're always sitting dark and cold, they continue to trap materials in that area, and it could make for some very interesting samples and chemistry on the lunar surface. If you're going to go explore that surface, then you want to know what it's going to do towards your rovers, your wheels, your boots. You also want to know how to handle the sample when it comes back. So if you saw our curators working with the OSIRIS-REx sample, we are working to learn how to handle those samples at ultra cold temperatures so that we can have them for study.
Okay, thank you.
Thanks, guys. Okay, I'm gonna ask the next question from the chat. This is from Jolene Schaefer. I don't know if I'm saying your first name right. I love this kind of question. Have you always wanted to work for NASA? And if so, what made you want to work there?
I think I always did. Growing up, and I don't know if it's still going. I think there's a space camp, camp activity that I always wanted to go to. Never quite got to it. And I always enjoyed working with, when I was in college and graduate school, lasers and vacuums and kind of weird environments. Earth, we know, it has, weather and it's not frozen all the time. But weird environments like vacuums combined with lasers means you can have different science effects occur. So I always enjoyed that part. The reason that I wanted to make sure to say that if you're interested in NASA, I want to tell you you can do it, is because I always thought, well, maybe I can't, or I'll go do something else, and so through fits and starts, I had the opportunity to work with various universities and small companies, and was doing that, and I got an opportunity to write a proposal for NASA for one of their postdoctoral programs, and that got accepted, and that's how I started getting to be involved with NASA. There are actually many roads to be involved at any time. There are proposals for companies and contractors to work with NASA. There are graduate programs and college programs called pathways. There are internship programs. So there are all sorts of on-road events for anybody that's interested in working with NASA.
That's great. Yeah, and you never know what's going to happen until you apply, right? So
Right.
Okay, I'm going to pass it over to Luke, who's got his hand raised. Luke, do you want to go ahead and unmute yourself and ask your question? Let's see. I'll ask him to unmute. Are you there, Luke? Are you there? Okay, there we go. Maybe. Oh, did he just go away? All right. Well, I have another question I can ask. Well, maybe Luke will come back. Okay, so another question in the chat from TMW. What materials have you added to regolith in the lab? So you talked a little bit about this to test or not regolith, maybe used for buildings on the moon. So maybe that's a question. What would you use to make a building on the moon?
It's a very good question. Let me see, hit my backup slides here. I'm feeling prepared.
Yeah.
So one of the things we can do is look at what's called the Planetary Simulant Database. And this is publicly available. So if you look at what's in regolith, it has silicates, aluminum oxide, iron oxide, magnesium oxide, all these different kind of various mineralogies. So this is the kind of material, if you wanted to build something out of only regolith, you could go to the Planetary Simulant Database and examine what those materials are there. I am not an expert in this with building with this kind of material, but from what I understand, there are methods for what's called sintering, where you heat up and fuse these materials into, for example, bricks, those kind of things. There are also other aspects called in situ resource utilization, where you can extract oxygen and water. Well, not water from the minerals, but you could extract oxygen from these and water from other sources to work with. There are some examples of people trying to make solar cells out of simulant. So that would be another aspect. If you could kind of grow solar cells. You asked about what we put into the regolith. And so one of the things that we're studying, if I can zoom in here. So we add water, methanol, ammonia, carbon dioxide, hydrogen sulfide. All of these different materials are potentially on the lunar surface or, within the near surface area. So those are some examples of the chemistries that we're studying. In brief, this was found from an impact study, and what happened is they took an extra stage and impacted it into the surface at a very cold temperature, and then they used spectra to guess at what the chemistries are on the surface. And so these are some of the materials that we're using to make our regolith.
Very cool. And if you guys notice, he's a chemist, so he knows when all those materials go from gas to water phase to ice phase. So, which is important when you're dealing with cold temperatures on the moon. Okay, Luke managed to get his question in the chat here, so I'm gonna skip up to Luke and ask his question. His question was, what steps would we have to take to get to Mars and possibly colonize? It's a big question.
That's a very big question, a very good question. So colonize, that's a whole nother story. There is talk about that in the commercial company sectors. You can probably find which company is talking about that. There's a few companies and organizations that talk about that. The challenge is that it's so far. It's so unbelievably far. The travel just to get to Mars is 6 to 9 months or so. And the amount of effort that it takes that it would take to ship people that have a whole lot of other requirements, unlike rovers that just have batteries and solar panels, for example. It's hard enough to do rovers at Mars, much less people. So if I may defer the colonization of Mars to another seminar, that would be good. What was the first part of Mars?
Well, it was just this main steps to get there, which I think you talked a little bit about. But you could
Ah.
maybe talk about how going to the moon will help us prepare how to get to Mars.
That is true. So that's another big aspect of Artemis, is learning how to be on the moon is going to give us practice for learning how to be on Mars. And one of the side challenges is not just being there. Humans, we need the ability to not only have food and water, but we have to have activities and those kind of things to keep us involved and going and busy and active. There's some physiological issues with being in space, such as if you don't move for a while in zero gravity, then you start to lose muscle mass. So for one challenge is, for example, going to Mars, if you spent 6 to 9 months weightless, you would have a hard time standing when you got there, for example. So if you've ever been on a really long road trip and then suddenly stop somewhere, well, just imagine 6 to 9 months of that.
Okay, great. All right, let's see. We've got another question. I will get to the next video. That'll be the next one. So hold your hand up there. Not Michelle, whoever's in Michelle's Zoom. But first I'm going to ask another question submitted through chat from EHT PAL, P-A-L. Maybe that's the school name. Let's see, you already answered that first question. So the first question was what materials do you use to make the simulant? I think you just discussed that. This is pretty specific, so it's okay if you don't know the exact answer, but how long did it take the DART mission to arrive at the asteroid? Do you remember?
I don't remember. I want to say, a year approximately. So I don't know exactly on that.
Yeah, it takes a while. It depends. The asteroid belt is a little bit further because that's just in the asteroid belt, right? So further from Mars. So yeah, depends on where everything is in its orbit.
Yeah.
Okay. I'm gonna switch it over to Michelle. Oh, no, I don't see him anymore. Michelle O'Very, you got your hand up. Do you want to unmute and ask your question?
Yes. Okay. So we have
10 months, by the way.
10 months. There we go.
I Googled it.
There we go. It worked.
My question is, how would you do the space catch without doing it before in space? Would you use sensors, or will the satellite stop to grab the pod which carries the samples and extracts?
I think that was Mars sample return mission. Yeah.
Is it Mars or was it the asteroid?
That is the Mars.
The Mars sample. And you said again, the space hatch?
Hatch.
What I'm sorry. What do you mean space hatch?
I think you said
space catch.
Oh, catch. So that video from the Mars aspect is a planning video also. Yeah, so the Jet Propulsion Laboratory are experts at the rovers and satellites. So I'm not exactly sure how they plan those, but I'm going to take a guess. So when you go towards the engineering side, there's an extensive amount of planning and calculations that goes on. One of the categories of engineers is orbital mechanics. And so you can run these simulations and calculations of doing the launches and transferring samples from one to the other using orbital calculations, which are just fancy way of calculating things in an arc. So once something's in gravity, it starts to curve instead of going in straight lines. If it was in straight lines, I agree, it would be much easier. But nature isn't listening to us quite yet. So I don't know if that answers your question, but there's a lot of planning that goes on. The Mars sample return is would be in the next decade or so. So that would be 10 plus years from now.
Okay.
Right. So some of you guys that are in middle school might be in college by the time that happens. So maybe you'll take an internship, help them out.
So
Good.
I have a question.
Go ahead.
So do we have a scheduled time for the samples, the Mars samples to come back with, yeah.
Yeah, that's a good question. It's currently 10 plus years.
Oh.
So it's just right in time for you all to show up and help. So what you see in the video is a series of rovers. What will happen is they'll put one rover down every so often and kind of get prepared for these missions. So currently there's a rover on the surface that's collecting the samples, and the next year, not next year, the next rover would be perhaps the one that gets ready to launch them and that kind of thing. So just like you do any project that you're doing now in school, it's done in stages. So I just wanted to make sure to say that it's what you're doing now is what we do, which we do one thing and then we do the next, and we try to get it all to fit together. But the planetary engineers do so.
Just like what you guys are doing with hopefully your rockets, it takes a lot of tests and re-engineering and changing things before NASA can be assured that it's going to work, right? If you're going to pay to send something all the way to Mars, it better work correctly. So that's what they're doing right now. They're planning and they'll build and they'll test, and they'll probably have to change it and build and test again and again until it's right. Okay, I'm going to ask related to that. And you are not an engineer, but you probably know some. So what do you, and this is a big question, so maybe I'll refine it a little bit. What is the main job of an aerospace engineer, maybe that works for NASA?
That's a great question. So, everyone is certainly talented. I get to interact with quite a few engineers, and so part of what I get to see is the interface or the way that scientists talk to engineers. And so it's very it's a very planned activity. So if you like to have a plan and a concept, an idea, and then facilitate that idea, aerospace engineering is a great activity and career to go towards. So I'm not fully aware of how the aerospace engineering is done, so I can give you a general idea. But it's a completely different ecosystem, completely different activity than science in a laboratory. And what I mean is when you get to see it in action, it's really quite phenomenal because everything is tracked. So in flight hardware, which is what things go to space, there's a thing called a technology readiness level. So it starts at 1 and goes to 9. And your basic prototypes and things that you do on a whim, maybe from 1 to 3. As you get better, those things that are really consistent might go to 4 to 6. The 7, 8, 9 levels, especially the 8 and 9 levels, are things that have been flown and are repeatable. So an aerospace engineer's job is to take things up the technology readiness levels and then make sure that they function the way they're supposed to function. And in order to do that, nothing can be random, or you have to minimize the amount of random. So every component is tracked, every bolt is tracked, every design is tracked. There are no hot wiring of stuff or last minute changes, because if something happens, the only thing you have are your records. So I hope I'm doing that justice. You could say that the aerospace engineers are kind of like the rocket surgeons of NASA. They're very precise.
That's a great answer to that. I like that. Okay, you guys are being shy in the video, so I'll keep asking questions for you from the chat, which is fine. Daniel X would like to know what your favorite geological region on the moon is and why, if you have one, a favorite geological region.
I am particular to the permanently shadowed regions. That's the most interesting. So as I was showing, let me see if I can find that slide. The permanently shadowed regions are really kind of the current exotic material of the lunar surface, because again, as they're so cold and they've been cold for so long, it's going to trap all sorts of weird chemistries and other things that add to the story of the lunar surface. So probably the permanently shadowed regions are a current favorite. I want to show you, well, one of my favorite pictures is again, here's what the dark South Pole sections of the moon look like, and it's not friendly. It is very bright or very dark and very cold, and so it's really kind of a challenge to be in this environment. A lot of people have spent significant time trying to figure out which regions to potentially land. So there are 13 regions that are potential landing sites for some of the upcoming Artemis missions. And so again, in those regions, you're going to have a lot of exotic kind of chemistries that could go on. And so the permanently shadowed regions are probably my favorite.
Very cool. Okay, hold on, my chat disappears. Every time someone shares their screen on Zoom, everything changes. Let's see.
Oh,
that's okay.
sorry.
No, it's not your fault. I just needed to wait for a second. Okay, more questions from the chat. This is a good one from Hannah Nickel. Which colleges do you recommend if you want to work at NASA as an astronaut or scientist? Oh, are you muted? Double check.
He's not muted on us.
Oh.
How about now?
Okay.
Can you hear me now?
Yep.
All right.
Weird.
Yeah.
We're all experiencing the joy of computers. There's 6 different ways this thing can mute itself. So we just have to be patient with each other. I appreciate y'all's patience. There's a side editorial there for life. I can't recommend a particular college or not. My background is I was able to attend a liberal arts college, got my Bachelor of Science, Texas Lutheran University in Seguin, Texas. And then I was able to go to Baylor University in Waco, Texas for physical chemistry. And for me, I found people and mentors that I enjoyed working with and resonated with. So instead of picking a particular college, which is important, I would also add into that finding people that you enjoy working with, or mentors that you resonate with and you feel like somebody listens to you and gives you good critical feedback. You don't want somebody that just tells you yes all the time. You want somebody to go like, yeah, you could do better. So that's the importance of a good mentorship. Now, that being said, you can look up colleges that are very strong in engineering and aerospace engineering. And then what I would do is, if you're of an engineer mindset, make a plan, make a checklist, and then go through those top 10 colleges and apply to those colleges, and kind of set your direction that way. Then when you're in college, remember that there's the NASA internship programs and also the NASA Pathways system that people are able to kind of start being working at NASA as an intern, and then they have the chance to continue on after sometimes. So I would recommend that.
Yeah, good advice. And while before you go to college, keep signing up for activities like this, NASA related activities, and that will help you get into whatever college you choose. But yeah, you'll find that lots of people from all kinds of colleges work for NASA. To be an astronaut, though, you do have to have a PhD, unless you're going to be a pilot. At least now. We'll see if that changes.
Is that a requirement? Yeah,
I think it is.
I'm sure.
That's from my own childhood research. Let's see here.
Sure.
I'm gonna switch to, let's see, Heather had a good question. It's okay, again, some of these are very specific, so if you don't know the answer, that's fine, because we all don't know everything. But are there any chemicals in the lunar regolith that are toxic to plants that you know of?
I think you would find the ammonia, the hydrogen sulfide, and the formaldehyde. Some of those lightweight organic kind of solvent compounds that you would find in like paint removers and other kind of, if it looks like an industrial chemical, then plants probably don't like it.
Okay, good. Okay, one more from the chat. Are you familiar with the Stardust mission to capture comet trail material? And if so, were the materials similar to those brought back by the DART mission?
So to clarify, the DART did not bring back any materials. That was the OSIRIS-REx. And so OSIRIS-REx is from Bennu, is a kind of carbon-based sample return. And so I believe those are significantly different than the Stardust mission. By the way, the Stardust mission, as part of Ares curation, one of our goals is to hand out materials to universities and researchers, and so people can actually request those kind of materials and study them. That is kind of part of NASA's stimulation of the research for the global research community, or at least the American community and its partners.
Thanks. Okay, let's see. Unless anybody else has questions up on the video, I think I've only got one more question here in the chat. So I'll ask this last, let's see, hold on, did one just pop up? Oh, so I'll ask this one last question, and then we will thank our speaker, excellent speaker today. This is one related to one of their mission objectives. So could you use regolith as a 3D filament to make structures? So do you know anything about maybe using regolith to build as a building material on the moon?
I think some of that is, so in 3D printing, you have typically a plastic or some kind of, when you say filament, it's on a spool and it's extruded through a hot nozzle. This is where I think a better analogy would be kind of the 3D metal printing, or perhaps the UV printing, where lasers are focused on a material and they fuse it or sinter it. So instead of a filament, I think there are some tests on using lasers to kind of 3D print objects out of the simulant.
Yeah, that's really cool. Yeah, if you guys do some research on 3D printers, there's some that you can get, where you just kind of laser material. I've never used one myself. Hopefully they work as well as the extracted ones. Have you? I don't know. I'm pretty new.
I have not. Yeah.
Okay.
I hope I gave a good kind of spectrum of all the different activities and all the different types of people working together. It's quite extensive. And so whatever your interest is, I'm sure there's a place to plug in. And as a note, I've always had good reactions reaching out to people, especially civil servants and contractors at NASA. If they don't know the answer, well, they will try to find somebody who does or who has contacts. So if you ever feel like you're stuck with a question, simply look up on the web who's doing that, and you can send them an email, or your teacher can send them an email, and they will be just joyed that somebody has reached out and asked them.
Yes, they love to know that someone cares about what they're doing every day.
Yeah,
right?
yeah.
Yes. All right. Well, thank you so much for joining us. I really learned a lot listening to you. All the participants, everyone, thank Dr. Lewis for taking the time out of his day to join us and answer your questions and tell us about what he does and what it's like to work for NASA. And yeah, I will go ahead and end it there. If you want to hang out, you can, or if it's time, you guys can go ahead and sign off. Thank you guys. Thank you for joining us. We look forward to seeing you soon and seeing your final Artemis Roads 2 submissions. Keep working hard.